A configuration redesign of the Saturn C-1 Space Vehicle Second, or S-4 stage, was one of several significant program changes occurring during the report period April, May, June 1961. Formerly, 4 Pratt & Whitney XLR 119 engines were to have been used, each developing 17,500 pounds of thrust for a stage thrust of 70,000 pounds. The S-4 stage will now be powered by 6 Pratt & Whitney engines designated as RL-10A3. Using liquid hydrogen and liquid oxygen, each develops 15,000 pounds of thrust for a total stage thrust of 90,000 pounds. At Douglas Aircraft Company, S-4 contractor, effects of the engine change are being absorbed into the program. In the manufacturing area, the bulkhead segment skins, which will be welded into the tank domes, were being formed on this Sheridan stretch press. The stretch forming method has proven to be the most practical, Douglas reported. After stretching, the skins were welded on this weld fixture, and then chemically milled to the correct thickness. This operation has been altered as a result of the engine change, since a greater internal tank pressure will be required. The chemically milled portion of the aft bulkhead has also changed due to a different point of tangency of the thrust structure, dictated by a larger engine mounting diameter requirement to accommodate 6 engines. Fabrication of the forward and aft interstage panels at Douglas Long Beach facility was not affected and is continuing on schedule. The first RL-10A3 mock-up engine was delivered to Douglas this quarter by Pratt & Whitney for necessary modifications, such as addition of a propellant utilization servo unit and forward and rear transducer boxes. Construction and modification of test facilities at Douglas Sacramento Division were not appreciably affected by the engine change. Fabrication of the 2 90,000-gallon liquid hydrogen storage tanks moved ahead during the report period. The inner aluminum sphere was thoroughly checked for leaks prior to its installation into the outer steel half shell. The leak test was accomplished by pressurizing the sphere and checking the welded seams with a helium detector probe. After leak testing, the top hemisphere of the outer shell was put into place. A helium sphere burst test was conducted at the Sacramento facility to determine the sphere's biaxial strength under loaded conditions. The test sphere was made in the same manner and of the same titanium material as the production items now being fabricated. The sphere was placed in a test container and submerged in liquid hydrogen, as it will be in the S-4 vehicle tank. Helium gas was then pumped into the sphere until burst occurred, as shown in these high-speed sequences. Predicted burst pressure was 9,500 psi, but the pressure reached 9,750 psi before the test sphere failed. Similar tests will be conducted on the production spheres. Tests were also made of the S-4 helium heater, which will pressurize the liquid oxygen tank in flight. After a series of cold flow tests and preliminary hot firings, a test was run to check the chamber ignition time. A propane torch was placed outside the chamber to ignite any escaping gas. At the beginning of the test, the heater ignited normally but went out, possibly due to a fuel-rich mixture. Unfortunately, the fuel supply valves were not shut off, and the serogenic propellants quickly cooled the ducting and began entering the combustion chamber as liquids. The propane torch supplied an ignition source. This blowout was not a setback to the S-4 program, however, since the heater had already successfully proven the concept. Work being done at the Marshall Space Flight Center on S-4 included this testing of a dummy stage to determine its mass moment of inertia. That is, reluctance to angular acceleration about pitch, yaw, and roll axes. The test is based upon application of the basic spring pendulum principle. The period of vibration for the stage, suspended on springs of known spring constants, is determined by a photoelectric cell and electric timer. The mass moment of inertia is calculated from this data, plus stage weight and center of gravity data obtained by electronic load cells in previous tests. In addition to the S4 engine change, approval was received this quarter for a Marshall Center proposal to establish a two-stage vehicle as the basic Saturn C1. This eliminates for the orbital mission vehicles the requirement for an S5 stage, shown here in dummy form. However, for special deep space missions, a modified Centaur stage could be used. The S5 dummy stage will be flown on the first 4 Saturn vehicles, but SA5 and subsequent R&D vehicles will have no third stage. In order to meet structural requirements for possible future Saturn missions, a number of redesigns will be incorporated in the booster for SA5 and subsequent vehicles. As shown in this 1/10th scale model, 4 large fins will be attached at the tail to increase flight stability. 4 so-called stub fins, actually support structures with aerodynamic fairing, will be incorporated to provide additional support points. These 8 combination arms will replace the 4 retractable support arms and 4 hold-down arms used in launching SA1 through 4. Tail shroud redesign from modified cloverleaf to cylindrical shape eliminates need to retract support arms for takeoff clearance. A plan to exhaust turbine gases of the 4 inboard engines by means of pipes through the 4 large fins is being considered to decrease the base heating rate. Another important feature of the SA5 redesign is the lengthening of the fuel and liquid oxygen tanks by approximately 6 feet, from 50 to 56, to accommodate some 100,000 pounds more propellant for a longer burning time. The S4 stage will be attached directly to the booster's spider beam, thus eliminating need for the present upper stage adapter. A honeycomb fairing mounted to the I-beams at 45-degree angles will be used to fare in between the 2 stages. Also mounted from the I-beams are the booster's 4 retro rockets and the 4 antenna panels. Indicative of continuing research efforts relative to Saturn, Marshall's engineers have been working recently on a new method of engine or explosives ignition known as the exploding bridge wire, or EBW system, designed to replace conventional ordnance items such as initiators presently used. Possible uses of the EBW, which may have application in the Saturn program, as well as in other programs, include ignition of engines on the ground, separation of stages, ignition of upper stages, and ignition of retro rockets. Designed to increase safety to personnel, the bridge wire is relatively insensitive to temperature and shock environments. Another safety factor is that it requires a tremendous amount of current within a very short period of time to cause the bridge wire to explode. The EBW firing unit has the capability of replacing 12 safing and arming blocks. The current in a typical EBW will rise to or exceed 500 amperes, depending on cable length and type, in 1 microsecond. The EBW will explode 1 microsecond after the energy is applied. Work moved forward at the Marshall Center this quarter on the first Saturn flight vehicle, SA1, scheduled for launch in October. As part of the booster flight qualification program, 3 static test firings were held, each generating some 1.3 million pounds of thrust. A short duration test of 30 seconds was conducted on April 29th with successful results. A second static test was accomplished on May 5th, scheduled as a long-duration firing. The test was terminated prematurely at 48 seconds because of a leaking pressure pickup. Designed to sense hot gas pressure, the pickup is part of the test equipment rather than of the booster itself, and the problem was therefore considered minor. Investigation indicated that the pickup could be disconnected for the next firing. A third and final static test was held in order to get a run to LOX depletion. This long-duration firing, 112 seconds, was successfully completed on May 11th. The next time these powerful engines are fired, they will actually push the mammoth Saturn vehicle into flight. The SA-1 booster was removed from the static test stand on May 25th and taken to Marshall's Fabrication and Assembly Engineering Division for necessary final modification and repair work. A final thorough 6-week-long checkout of this initial flight booster began on June 12th in Quality Division. Preparation for shipping to the Cape Canaveral launch site is due to start in early August. The Saturn barge, Poleman, has now been modified to accommodate either an S4 or S5 stage behind the booster, so both can be shipped in one trip. In a trial run, the Poleman left Marshall on April 17th, carrying a booster simulator with water ballast and the S5 dummy stage, which will be flown on SA-1. The barge reached the Cape safely on April 30th, although it had been delayed several days after suffering minor damage in a collision with a tanker near New Orleans. The Poleman ended its return trip to home port on May 15th to await its scheduled August departure date, carrying the first flight booster and dummy second stage. However, on June 2nd, the collapse of a lock of the TVA's Wheeler Dam, through which the barge passes on its Tennessee River route, caused a quick change in plans. The Poleman will now carry the Saturn stages from Marshall to the dam, where they will be hauled overland about a mile around the dam, then reloaded onto a specially modified Navy barge for the rest of the trip. After the dam is repaired, the Poleman will make the entire voyage. Saturn launch equipment, consisting of these support and hold-down arms and short cable masts, underwent testing as a complete system this quarter at Marshall. Individual components had been tested previously. The short cable masts provide electrical and pneumatic service for the booster and launcher accessories for pre-launch checkout and launch. Upon thrust commit, they are pneumatically disconnected and pushed away. Upon disconnect, an electrical signal is sent to the support arms to begin retraction. These slow-motion scenes show how the system would operate during a normal Saturn launching. The entire sequence takes place in 4/10 of a second. This malfunction test was also run, simulating conditions in the event the booster fails to generate full thrust. Shown in slow motion, the support arms begin retraction, then return to the support position without signaling the hold-down arms to release the booster. This action requires 9/10 of a second. Following successful tests, the equipment was sent to Cape Canaveral for installation on the Saturn launching pedestal in preparation for the first firing. At the Saturn blockhouse or control center, installation of interior equipment such as racks, panels, consoles, and wiring was accomplished. And on June 5th, the 2-year-long construction program on the massive 45-acre Saturn launch facility was declared completed, and Complex 34 was officially turned over to NASA by the Army Corps of Engineers. At the Marshall Center, work proceeded this quarter on assembly of the booster for the second flight vehicle, SA-2. Begun in December of 1960, the booster is slated for Quality Division checkout in August. Fabrication work on SA-3 is continuing, with assembly scheduled to begin July 31st. The Saturn test booster, called SAT, underwent modification this quarter to make it identical to the SA-2. Following completion, a new series of static test firings began in late June. Construction on Marshall's new 204-foot-tall dynamic test tower, in which Saturn stages will be excited to simulate flight conditions, was finished in mid-April. On May 9th, the dynamic test booster, known as SAD-1, was emplaced in the tower. Assembly work on the booster was completed here, while the test facility itself was being instrumented. Early in June, the S4 and S5 upper stages were also installed in the tower and attached to the booster. Dynamic vibration tests conducted by the Structures and Mechanics Division are scheduled to start in July. The stages will be filled with water to simulate liftoff weight conditions. After completion of S&M tests, the vehicle will then be turned over to Marshall's Test Division for further test programs in September.